Dear students, under the topic complex analysis, now we are going to learn about limits. There are various definitions for limits. I will take a formal definition and I will explain it to you. So here we have a definition which says that if a function f of x is a complex function, then the limit L of f of x at the point z0 is defined as limit z tends to z0 f of x is equal to L. That is, if we have a complex function z which tends to z0 in a plane, then the function of this complex variable will tend to a limit L. Then L is said to be the limit of the function of the variable z. And always this limit will be a unique value. That is, it will be a single value along any path. Let me explain it better to you. So when the limit of a function f of z exists as z tends to z0, then that limit will always be unique and L will be independent of the path. Now let us see the geometrical explanation of this. That is, what is a path? So now geometrically representing it, we consider the point z in this plane, and this is the origin which is z0. Now this point we know that it is x comma y, and now when this z tends to z0, that is, it takes a path from z to z0. Now this path I have drawn as a straight line, but it's not necessary that the path should only be a straight line. It can also be a curve. It can also be an irregular curve like this, or it can be another curve of this type, or you can also travel from this point to this point along the axis. That is, you can go to x-axis, and then along this axis you can travel and reach to this point. In a similar manner, you can reach this y-axis, and along y-axis also you can reach the point z0. So the path, there are different paths that we can take as z tends to z0. But remember, if the limit exists, then always the limit will be unique. Whichever path we choose, irrespective of the paths, the limit f of z will always tend to L only, as z tends to z0. If this limit is not unique, if you consider this path and you find a limit and another path and you find a different limit, then it means that the limit does not exist. So always remember, if the limit exists, then it has to take a unique value. If it does not take a unique value along different paths, then the limit does not exist. So that is the concept of limits under complex analysis. Now using this concept, we will solve some important problems. Now before diving into the problems, let's understand the concept of paths also. Now I told you we can reach the point z0 from z along the x-axis, which means, so along x-axis. So along this x-axis, we know that always y is equal to 0, because along x-axis every point, if you check, the value of y will be 0. And since z tends to z0, x will tend to 0, but y will be equal to 0. Similarly, along y-axis, if you consider, x will be equal to 0 and y will tend to 0. You will understand this concept when we deal with the problems. And there can be different paths also. If it is not along the x-axis or y-axis, it can be a straight line. So, if the path is a straight line, what will be the equation? We know that the equation of a straight line is y is equal to mx. And if it is not a straight line, it can be a parabola. The parabola can be of this type or it can be of this type. So the equation of the parabola differs here. So if it is a parabola, then what are the equations that we can imagine? We can say that x is equal to my square or y is equal to mx square. We can also say that y is equal to square root of x or y is equal to 1 by root x. These are different curves. And similarly, we can have some cubic equation also. For example, it can be a cubic parabola. We call it as cubic parabola, which will be y is equal to mx cube. It can be of this type also. So we can imagine different paths so that z can reach z naught using different paths. But if the limit exists, all the limits will be unique. If the limit is not unique along these paths, then it is it implies that the limit does not exist. And you can imagine this curve y is equal to mx cube in this manner. That is, the curve looks, it sketches like this. Okay, now we shall solve problems under this topic. Now, here in the question, we have the first problem as prove that the function f of z equal to z bar divided by z does not have a limit as z tends to 0. Now, in order to prove that this function does not have a limit, it is sufficient to prove that the limit which exists for different paths is not unique. Because we know that if the limits are not unique, then the limit does not exist for that function. So for that, we shall consider different paths for this function. First of all, we shall write the function f of z, which is equal to z bar divided by z. In our previous video on complex functions, that is functions of complex variable, I have already explained you that the complex variable z is taken as x plus iy and its conjugate is z bar, which is equal to x minus iy. Now z bar can be written as x minus iy divided by z is x plus iy. Now we have to check for the limits. Now, in order to find the limits, we can consider different paths. I have already told you about the different paths. First, we saw along the x-axis, along y-axis, and different curves. I would suggest that you can consider a general curve in order to prove this. Now, we can consider along the straight line y is equal to mx. So along y equal to mx, we know that f of z will be equal to, now at the place of y, we have to replace it with mx over here. So it will be x minus I multiplied with mx divided by x plus I multiplied with mx. So this will be equal to, we can see that x is common in both the terms. So it can be written as x multiplied with 1 minus im divided by, x is common in both these terms. So we can take it out and it will be 1 plus im. And we see that this x and x gets cancelled. Now we will take the limit. So limit, we have z tends to z naught. So limit z tends to z naught of f of z will be equal to, now since we do not have the z term over here, it will be as it is. So 1 minus im divided by 1 plus im. Now the limit depends upon the value of m. So limit depends upon the value of m. So as the value of m changes, the limit also keeps changing. Now let us just test it for few values of m. That is, if we take m is equal to 1, what will be the limit? It will be 1 minus I divided by 1 plus I. If you put m as 1, we get this. What about m is equal to 2? If we put m as 2, we get 1 minus 2i divided by 1 plus 2i. If you put m as 3, we get 1 minus 3i divided by 1 plus 3i. So it is obvious that the limits are different for each values of m. So as the value of m keeps on changing, the limits are also changing. But we know that in order to for the limit to exist, the limit should be unique. But Here we see that the limits are changing as the values of m are changing, which means that the limit is not unique. So this implies that the limit is not unique. So if the limit is not a unique value, then we say that the limit does not exist. So therefore, the function f of z equal to z bar by z does not have a limit as the z tends to 0. So hence we have proved the required result. So I hope you would have understood how to prove that a complex function does not have a limit. Here we have the next problem, that is prove that f of z equal to x square y square divided by x plus y square the whole cube for z not equal to 0 does not have a limit as z tends to 0. So we have to prove that this function f of z does not have a limit, for which we have to consider a path. So the path that we will be considering will be a parabola y square equal to mx. The reason is we have y square in this term, and here also we have y square. So it can be easily replaced as mx. So we are going to consider a parabola y square equal to mx as the path. So along this path, f of z will be equal to x square multiplied with, now y square is taken as mx divided by x plus y square is mx the whole cube. So the numerator turns out to be mx cube divided by, here we can see that x is common in both the terms, and so we will be having x multiplied with 1 plus m the whole cube, and this can be further written as mx cube divided by x cube multiplied with 1 plus m the whole cube. And so therefore f of z is equal to, this x cube and x cube gets cancelled, you will be having it as m divided by 1 plus m the whole cube. So now when you consider the limit z tends to 0 of f of z will be equal to, since you don't have a z term over here, it is just m by 1 plus m the whole cube, and this value depends on the value of m. So as the value of m changes, that is when m is equal to 1, this will be 1 divided by 2 cube, which is 8. And when the value of m is equal to 2, what do you get? The limit you get as 2 divided by 1 plus 2 is 3. 3 cube is 81. And we see that the limits are different. They are not same. So which means that the limits are not unique. The limits are not unique. And if the limits are not unique, then the limit does not exist for this function. Hence we have proved that f of z does not have a limit as z tends to 0. So hence we have proved the required result. We will solve some more problems on this topic. Now here we have problem 3. In order to prove that this f of z equal to square root of modulus of xy divided by x plus iy does not have a limit, let us consider a path. So let us consider the straight line. So consider the path along the straight line y is equal to mx. So what will happen to f of z? It will be equal to square root of modulus of, now at the place of y we have to replace by mx. So x multiplied with mx the whole divided by x plus I multiplied with mx. In the numerator it will be equal to square root of modulus of mx square divided by, this x is common in the denominator, so it will become 1 plus im. So what is square root of x square? It is x, and square root of m we will have. Since it is modulus, it won't be plus or minus, it is just x divided by x multiplied with 1 plus im. So x and x gets cancelled and it's equal to square root of m divided by 1 plus im. So therefore what will happen to the limit? So limit z tending to 0 of f of z will be equal to, since there is no z, it will come as it is, square root of m 1 plus im. and this value of the limit keeps on changing as the value of m changes. That is, when m is 1, what it will be? It will be 1 by 1 plus I. And when the value of m is 2, it will be square root of 2 divided by 1 plus 2I. So the value of the limit keeps on changing as the value of m changes. Therefore, the limit depends on m, and the limit is not unique, and hence the limit does not exist. Hence, we have concluded that f of z does not have a limit as z tends to 0. Now here we have the next problem where f of z equal to xy by x square plus y square. Now we will consider the path y equal to mx. So what will happen? We have to put y equal to mx over here. So x multiplied with mx divided by x square plus m square x square, because y is equal to mx, so y square will be m square x square. In the numerator you will have mx square divided by x square plus m square x square. So you can take that x square in the denominator common, it will become 1 plus m square. So this x square and x square gets cancelled and you get m by 1 plus m square. We see that the value of the limit depends on the value of m. So limit z tends to 0, f of z equal to m by 1 plus m square. So when m is equal to 1, what do you get? You get 1 by 2, because when you substitute m as 1 here, 1 plus 1 is 2. When m is equal to 2, it will be 2 divided by 2 square is 4, 4 plus 1, 5. We see that you have two different values. Therefore, when the value of the limit depends on m, and the limit differs as the value of m changes. Therefore, the limit is not unique, and hence the limit does not exist. So therefore, f of z does not have a limit as z tends to 0. Now here we have the last problem of this session. Prove that f of z equal to minus I x cube y by x power 6 plus y square for z not equal to 0 does not have a limit as z tends to 0. So now for this we have to consider the path where we are going to consider the cubic parabola y equal to mx cube. The reason is you can see cubic terms over here, and this is square of a cubic term. So therefore, if you choose y equal to mx cube, it will be convenient for us to proceed the problem. So therefore, I am going to choose the cubic parabola y equal to mx cube, where the curve is of this type. Yes. So choosing y equal to mx cube, let us substitute it in f of z. So that will be equal to minus I x cube multiplied with mx cube, the whole divided by x power 6 plus y square. So it will be m square, and x cube square will be x power 6, because x cube the whole square is 3, 2 times is 6. And so you can see that in the numerator it turns out to be minus I m x to the power 6 divided by, because x power 6 multiplied with x power 3 multiplied with x power 3 gives us x power 6. In the denominator x power 6 is in common, and you get 1 plus m square. X power 6 and x power 6 gets cancelled, and you have minus im divided by 1 plus m square. And so further, limit z tends to 0 of f of z is equal to, this is independent of z, so it will come as it is, minus im by 1 plus m square. And when m is equal to 1, what do you get? The value of this limit as minus I by 2, because when m is 1, 1 plus 1 is 2. When m is 2, it will be minus 2I divided by 2 square is 4, 4 plus 1 is 5. We see that the limits are becoming different. So for different values of m, the limit value also keeps on changing, which means that the limit depends on the value of m, and therefore the limit is not unique, and hence the limit does not exist. So therefore, f of z does not have a limit as z tends to 0. So I hope you would have understood the concept of limits. In our next video, we will learn about continuity in complex analysis. Thank you.